In this video, we'll be looking at nomenclature, which is writing formulas and names for compounds. So when we talk about nomenclature, it's kind of a big word, but what it really just is it's a systematic way of writing names and formulas for compounds. When we think about all the elements on the periodic table and different ways they can bond and combine, you get a very, very large number of different compounds to exist. We have to have a way to communicate information. That goes for every discipline. Chemistry is no different. So for us, nomenclature is our system to clearly communicate chemical information. And it's important, just like any other communication tool that you use or trying to relay information, everybody has to be on the same page. Everyone has to understand the same words mean the same things. Without that, it's very tough to communicate effectively, whether just in regular spoken language or to kind of convey scientific knowledge. So in this course, we'll learn the rules for writing formulas and names for basic chemical compounds. So there's two different types of compounds that we'll be dealing with. We'll be dealing with ionic and molecular compounds. We'll start with the ionic compounds. Ionic compounds get formed from positive and negative ions. It's that attraction between the positive ion and the negative ion that keeps the different components together to form that compound. When we think about what type of elements form each type of ion, well, what we saw before is that our positive ions usually come from metals. Our negative ions usually come from nonmetals. So when we're looking at an ionic compound, if you're seeing a metal and a nonmetal, that's your clue that you're dealing with an ionic compound. Later on, we'll deal with covalent compounds, which are not formed from ions. Here, you get a sharing of electrons keeping the pieces together. And your hint for dealing with these is you'll have different types of elements involved. You'll have two nonmetals that are bonded together. So let's start with kind of our rules for naming ionic compounds. You'll see this slide quite a bit in this presentation as we kind of go through the rules. But first couple of examples we'll do just deals with the first two rules. We'll always name the positive ion first, and you're going to see that we keep the name of the element. Then we'll name the negative ion second. What you'll see is we'll end up replacing the ending of that negative ion with IDE. We'll chop off the name of the element, replace it with IDE. We'll have some special rules for number 3 for dealing with transition metals. We're going to use Roman numerals to indicate the charge, because remember, those can have multiple different charges. And then lastly, we'll deal with the polyatomic ions. Polyatomic ions are going to take some special rules. We'll see some parentheses having to be used in order to effectively group them. Before we can kind of get into nomenclature, we need to do a little bit of a review, not necessarily with the names of the specific groups, but the charges. So we've seen this slide before, but here we're not going to focus on the names. Here we have to focus on the charges. So we want to do this quick review to go through those. Group 1A, positive 1 ions. Group 2A, positive 2 ions. All of these B's in the middle, those are those transition metals. Remember, we're going to have a special rule for those because they form positive ions of various charges. Things in group 3A, we're going to see form +3 ions. Group 4A, we won't see a lot of ions coming from that group. Group 5A, though, remember now we're kind of in the nonmetals. We're going to start seeing negative ions. -3 ions for group 5A. Group 6A, -2 ions, group 7A, the halogens, -1 ions, group 8A, noble gases. They're not going to form ionic compounds because they don't form ions very easily. So we're going to use this information quite a bit today. You have to have memorized which ions are going to get formed from which groups. And again, you see it kind of on the periodic table again. Things in group 1A, +1, 2A, +2. All of these in the middle are transition metals plus something. We'll have to figure that out. Then when we get into group 3A, +3, 4A, usually not a lot of ions get formed. Group 5A, -3, group 6A, -2, group 7A, -1, and lastly group 8A, not a lot of ions are going to be formed there. So again, here are our rules. In our first couple examples, we'll just deal with Rule 1 and Rule 2. We won't have to get into worrying about Rules 3 or Rules 4 just yet. So for our first example, to kind of illustrate this, I wanted to use an example that you're already familiar with. Many of us already know the name of this compound. We already know what this is called, but we want to go through the full rules so you can kind of see where that comes from. How does this apply to the rule? Then even things you're not as familiar with, you're just going to be able to use those rules in order to correctly name those compounds. So first, NaCl. First, are we dealing with an ionic compound? Remember, you can tell by the elements that are involved. When you look at sodium on the periodic table, you'd recognize right away that's a metal. Sodium's a metal, chlorine's a nonmetal, so right away you're definitely sure you're dealing with an ionic compound. So being we have an ionic compound, we want to think about ions. Now, even for the simple examples, I can't stress this enough or encourage you to do this any more than the great amount I can. This is really, really important. Write out the ions that you have. Anytime you have an ionic compound, I want you writing out the ions that you have. It makes the whole process of nomenclature so much easier. Even if you think you can see it right away without doing it, you really want to do this for yourselves. Nomenclature is one of the more challenging topics that we do, and writing out the ions is a way to make it a little bit easier and take a little bit of that challenge away. So all of our examples for ionic compounds, we're not just going to write out the name, we're going to write out the ions that we have. When you're able to look at the ions, things get so much easier. So let's look at these ions. We know these are going to form ions because we have metal and a nonmetal. So let's start with the sodium. We look at sodium on the periodic table. Sodium is in group 1A. That's going to make a +1 charge. We look at chlorine on the periodic table. When you look at chlorine on the periodic table, it's in group 7A. We said things in group 7A form a charge of -1. So now we have the ions that we need. These are the ions that we have. Now we can name this. First rule says write the name of the positive ion first. Keep the name of the element. So Na is sodium. Name the negative ion second. Negative ion, you replace the ending with IDE. So instead of chlorine, we're going to take off the ending of chlorine. And instead of using the INE ending, like the name of the element, we replace that ending with the IDE. So this is our name of our element, or name of our compound, sorry, sodium chloride, just what you're familiar with. Couple things to notice about this one, and we'll point this out. Notice the idea of charge balance in this. We have the same amount of positive charge that we have of negative charge, +1, -1. Also notice that our name doesn't contain, when we just say sodium chloride for the name, it doesn't contain any of the prefixes or any overt way of telling how many of each compound of each element are present in that. So we'll see that again in the next couple of examples, that there's no overt, prefix or anything that tells us the number of each ion, and that idea of charge balance. That's a recurring theme in these ionic compounds. So let's name another one. So K2O is what we're looking at, and first we want to say, is this an ionic compound? Well, we look at potassium on the periodic table, and potassium on the periodic table is in group 1A, that's a metal. Oxygen's in group 6A, that's definitely a nonmetal. And so we have metal, nonmetal, we're dealing with an ionic compound. Notice the subscripted 2 that you see between the potassium and the oxygen, highlighted in green. We use subscripts in our formulas in order to indicate how many of each element that we have. And the subscript always belongs to the element that came before it. So what this is saying is that we have 2 potassiums, 1 oxygen. We see subscripts over and over again. They're always going to have the same meaning. How many of what came before it? So now, just like before, we want to write out what ions we have in place so we can look at them directly when we're going through this naming. Here, remember what that 2 tells us. That 2 tells us we actually have 2 potassiums. Potassium is located in group 1A. Things in group 1A we saw had a +1 charge, so each potassium would have a +1 charge. We have 1 oxygen. Oxygen is located in group 6A. Things in group 6A have a -2 charge. Notice that idea of charge balance again. My sum total of positives is +2, 2 potassiums at 1 each. Sum total of negatives is -2. So now when I write the name for this, I always start with the positive ion. Positive ion keeps the name of the element, that would be our potassium. Negative ion, we chop off the ending and replace that ending with the IDE ending. So this is going to become oxide. And our name of our compound we're looking at is potassium oxide. Again, a couple things to notice in this. In the name, we're not using any prefixes. There's no overt indication that you're dealing with 2 potassiums and 1 oxygen if you just look at the name right away. The other thing you want to notice is that idea of charge balance. The same amount of positives as negatives, and we can see that in here. +1 and +1 make +2 for a total. That balances out with the -2 from the negative ions. So you're going to see that charge balance again. When we look at our next example, MgBr2, so now we want to name this compound. First, are we dealing with an ionic compound? Well, you look at magnesium, that's definitely a metal when you locate that on the periodic table. Bromine is a nonmetal. So we do have metal and nonmetal present in this, so we're dealing with an ionic compound. And just like every other ionic compound we're going to name, we're going to write out which ions we have and how many of them, so we can directly see them. It makes this process of nomenclature much, much, much more straightforward. So I have 1 magnesium ion, and when we look at magnesium on the periodic table, magnesium is in group 2A. Things in group 2A have a charge of +2. I have 2 bromide ions. I have 2 bromines here. Bromine lives in group 7A on the periodic table. That means each bromine will have a charge of -1. Notice that charge balance happening yet again, +2, -2. Same amount of positives as negatives. So now I'm ready to name this compound. Positive ion first. So we get our magnesium in. Negative ion second. Chop off the ending and replace it with IDE. So instead of bromine, that's going to become magnesium bromide. You're going to get that IDE ending in here. So the name of our compound, magnesium bromide. In this example, we're going the opposite way of the way we went with the previous ones. In the previous ones, we started with a formula that we had to write the name for. This way, we're going to do almost the exact opposite. We're starting with a name, and we're going to write the formula. And you want to make sure you're able to do this both ways. You want to be equally good going each way. So I want to show you an example going this opposite way. You're still using these same rules. And here's where writing out the ions really pays off. You can really see why that's such a good idea to do, because it just takes a lot of the kind of guesswork and other things out of it. You're able to look at what you have. Well, first, are we dealing with an ionic compound? Well, calcium's a metal. Nitride comes from nitrogen. We find nitrogen in the periodic table. That's in group 5A. That's over there. It's nonmetal. We have metal, nonmetal. This is going to be an ionic compound. So what do we need to do? We need to write out what ions do we have in place. We really want to be able to look at and see our ions. So calcium, we know, is in group 2A. Things in group 2A have a charge of +2. Nitride, well, that came from nitrogen. That's from group 5A. We said things in group 5A have a charge of -3. Remember, whether you write 3 minus or -3 doesn't matter. +2, 2 plus doesn't matter. So now when we look at this, do we have charge balance? And the answer would be no. I have a total of +2 for calcium and -3 for nitrogen. I don't have charge balance. I have an unequal amount of positive and negative charge right now. Well, there's a couple different ways that this could be fixed. Some of which you can do, some of which you definitely cannot do. So kind of the easiest one is something you can't do. The easiest fix would be, what if we just change the charges of these things? Well, if we make calcium +3, then we'd have charge balance. Well, we can't make calcium +3. Calcium does not form that ion. Calcium only forms +2. Or maybe we could change the charge on the nitrogen. If we made the nitrogen -2 instead of -3, well, we'd have charge balance, but that's not what nitrogen does. Nitrogen's not going to form a -2 ion. Nitrogen has to form a -3 ion. So we can't just change the charges of these. These form specific and set charges. But if we can't change the charges, we still have to achieve charge balance somehow. The only way to do that is, if we can't change the charges, we have to change the relative amounts of each. That we can do. So there's a couple techniques at this. You can do this. One technique is very mathematical. It's least common multiple. I'm not going to do it least common multiple. I'm going to show this kind of with the most simple way. It doesn't really involve much math. It's just the idea of trial and error. Look at what you're short of and start adding on those things that you're short of. So when I first look at this, I'm at a total of +2 and -3. I'm short positives right now. So what am I going to do? I'm going to tack on another positive ion. Now if I look at the total, I'm at +4 for my positive charge, -3 for my negative charge. Well, now I'm short negative charges. What am I going to have to do? Tack on another negative ion. Now I'm at +4 for my positive charges, -6 for my negative charges. Now I'm back to being short positives. Well, what can I do? I can tack on another positive ion. Now I look at my total of positives and negatives. My total positives are +6. My total negatives are -6. Now I have charge balance. So now I have equal amounts of positive and negative charge. So now I can just write my formula. Well, positive ion comes first, that's the calcium. How many calciums do I have? Well, I have 1, 2, 3 calciums. Negative ion comes second, that's the nitrogen. How many nitrogens do I have? 2 nitrogens. So my final formula is Ca3N2. Notice how in the formula we're not rewriting the charges in the formula. That kind of gets messy and sloppy. Remember, nomenclature, we're supposed to convey information quickly, easily, and thoroughly. If you start throwing charges in that formula, it starts to get messy on the reader to kind of look at it. It's too much to look at. Just like in the previous examples, if you go back, we didn't start with any charges in that formula. So here's our formula for calcium nitride. So we kind of did the first 2 rules for dealing with naming of these ionic compounds. But one of the things you would have noticed is none of the examples that we have done already involve the transition metal ion. Now it's kind of time to start dealing with these transition metal ions. Now we have to get Rule 3 involved. And this Rule 3 applies for transition metal ions only. What we're going to see we're going to have to do is we're going to have to use a Roman numeral to indicate the charge that that transition metal ion has. Remember, when you're looking at the periodic table where your transition metal ions live, they live in the middle of the periodic table. So you're looking at in here. These down here, we won't really see any of these down here, but these would also be transition metal ions as well. But generally, you're looking at the ones in the main part of the periodic table. So anytime you see any of the elements in here in your ionic compounds, you're going to have to follow that transition metal ion rule. So let's look at some examples that use this transition metal ion rule. And I kind of want to just do these 2 examples side by side in parallel so you can kind of see the importance of this rule that we're going to have. So first, are we dealing with ionic compounds? And if we look at the one on the left, I have copper. Copper is definitely a metal. It's a metal we're familiar with. Bromine is definitely a nonmetal, so this is an ionic compound. What do you want to do with your ionic compounds? You want to write out what ions you have in place. Well, what ions do we have in place? Well, I have a copper ion. Well, for this copper ion, when you look at copper on the periodic table, you're going to say, it's a transition metal. We don't know the charge of the copper from looking at the periodic table, so I can't put a charge in there just yet. I'm going to have to figure out what that charge is. When I look at the bromide, though, I do know something about the bromide. Bromine lives in group 7A, so I know what type of ion the bromine is going to form. It's going to form a -1 charge. I have to use that information. I still need charge balance. I'm using that information from the bromine now to figure out what the charge on the copper is. I have 1 copper and 1 bromine. And if the bromine is negatively 1 charged, that means the copper must have a positive 1 charge. That's the only way to achieve charge balance. Remember, I didn't get this plus charge from copper from the periodic table. I had to figure that out based upon what is happening with those negative ions. So now I'm ready to kind of write the name of this. Positive ion first, I have my copper. Negative ion second, the bromine is going to change into bromide. So right now, before I start using that third rule, I'm going to hold off for a moment using that third rule till I do the example on the right-hand side. I would just have copper bromide. Now if I look at the example on the right-hand side, I'm going to get that one to the same point we were at on the left-hand side before we start applying that third rule. Do I have an ionic compound? Yes. Copper's a metal, bromine's a nonmetal. Write out the ions that you have. So I have a copper ion. And again, I don't know the charge of the copper just by looking at the periodic table. It's there in the middle. I don't know what charge that's going to form. I'm going to have to figure it out. I know I do have 2 bromines, and I do know the charge on the bromines. It's -1. So now I have to use that information in order to achieve charge balance. My sum total of negatives is -2. I have to have a sum total of +2 from the positives, and I only have a single copper that can generate that. That means for this compound to have charge balance, this copper has to have a charge of +2. So now we're ready to write the name for this. Positive ion first, negative ion second. I'd have copper bromide again. And here's where you see the problem where just the first 2 rules that we talked about previously aren't good enough. At this point, I have the same name for both of these compounds. These compounds are very different. They have different physical properties, things like color, melting point. They have different chemical properties, how they're going to react. Even though they're both made up of copper and bromine, they are very different compounds. We need to have a way to distinguish one from the other. And that's where that third rule comes in. You have to apply this rule when you're dealing with transition metal ions. And that rule says that for transition metal ions, use a Roman numeral to indicate the charge that the transition metal ion has. So let's look at the example on the left. The copper has a charge of +1. So that means I'm going to have to use a Roman numeral 1 to describe what's happening with the copper. If I look at the compound on the right, what charge does that copper have? That copper has a charge of +2. So I'm going to use the Roman numeral 2 in order to indicate that. Using the Roman numerals gives us a way now to differentiate one from the other. Now we can clearly say which one we're referring to. So these transition metals and the Roman numerals, this is what starts to add a little bit of complexity and difficulty to dealing with the nomenclature compared to what we were dealing with before. The key thing with the Roman numerals is knowing what the Roman numeral is telling you. The Roman numeral does not tell you how many coppers there are. That's why we don't use regular numbers for that. We're using Roman numerals. What the Roman numeral is telling us, the Roman numeral tells us one thing and one thing only. And what the Roman numeral tells us is what is the charge of the copper. Copper's +1, Roman numeral 1. On the right-hand side, what is this Roman numeral telling us? It doesn't tell us we have 2 coppers because we don't. It's telling us what is the charge. So that's kind of one of the pitfalls that you can fall into doing these, is mistaking the Roman numeral for telling you how many of that element you have. That's not what it's saying. It's not telling you how many. It's telling you what is the charge of that transition metal ion. So we'll do some more examples so you kind of get a chance to see this in action. So again, we'll kind of do 2 side by side in parallel so you can kind of see how this ends up working. This time I'll just complete the one on the left and then we will complete the one on the right. So on the right, FeO. Well, are we dealing with an ionic compound? Well, we are dealing with an ionic compound. Iron is a metal. Oxygen is a nonmetal. This will definitely be an ionic compound. So when you have an ionic compound, we want to write out ions. So what ions are we needing to write out for this? Well, we need to figure out we have 1 iron ion. When you look at iron on the periodic table, you're going to see it's a transition metal ion. Just from looking at its position on the periodic table, we don't know its charge yet. We're going to have to figure that out from other information. Let's look at the oxygen. Oxygen we do know something about. Oxygen lives in 6A. When things in group 6A form ionic compounds, they're going to form -2 ions. We need to use this information to achieve charge balance. So the only way we could have charge balance in this compound is if the iron was also +2 in order to achieve that charge balance. That's the only way. So now we're able to name this compound on the left. Positive ion first, that's the iron. Negative ion second, take out the ending, replace it with IDE. And now, since iron is a transition metal ion, we need to use the Roman numeral in order to indicate what the charge of that iron is going to be. The charge on the iron is +2, so we need Roman numeral 2 here. Remember, that 2 is not telling us how many ions. That's not what the Roman numerals say. The Roman numerals tell us what is that charge. The charge on the iron is +2. Now, let's look at the example on the right, Fe2O3. We'll go through the same procedure on this one. Do we have an ionic compound? Yes. Iron is a metal. Oxygen is a nonmetal. Metal and nonmetal are going to make ionic compounds. So let's write out the ions that we have. Here I have 2 iron ions. So the subscript 2 is telling me. I don't know their charge yet. I'm going to have to figure that out. I have 3 oxygen ions. Oxygen lives in 6A. We know something about this. Everything in group 6A will have a charge of -2. So now I need to use this information in order to figure out what charge the iron has. Remember, my sum total of positives and my sum total of negatives have to balance each other out. I have to have that charge balance. So where am I at? If I count through all my negatives, -2, -4, -6, I'm at -6. That means my sum total of positives has got to be +6. So how can I get a sum total of +6? Well, if my sum total needs to be +6, that means each individual iron has to be +3. +3 and +3 would give me +6. That would balance out with the -6 that are coming from the oxygens. So that's how we determine that the charge on this iron is +3, by using charge balance and what we knew about the negative ions. So now we can write the name of this. Positive ion first, that's iron. Negative ion second, replace the ending with the IDE ending. And now, since iron is a transition metal, we need to make sure that we use a Roman numeral to indicate what charge it has. And here you might be tempted to put +6. Well, that's not the charge that the iron has. +6 is the total charge. You just list what type of iron we're dealing with. The type of iron that we're dealing with is iron that has a charge of +3. Remember what your Roman numerals are telling you. Kind of back on the left. What's our Roman numeral telling us? That Roman numeral 2 told us we had a charge of +2. What's that Roman numeral on the right telling us? Well, that +3 matches that Roman numeral. Remember, that's the definition of what the Roman numerals mean, what they're telling us. It's not how many, it's what is the charge. That is the question that they answer. The Roman numerals are always tied into the charge of those transition metal ions. We want to do an example going the opposite way. So the previous ones we did, we had the formula, we had to write the name for. This one we're going to go the opposite way. We're going to go from name to formula for these. So still ionic compounds still have transition metals in them. How do we know we're dealing with an ionic compound? Well, we look at what we have. Well, manganese is a metal. Sulfide comes from sulfur. Sulfur is a nonmetal, so we're definitely dealing with an ionic compound still. Remember, what do we want to do every time we have an ionic compound? Every time we have an ionic compound, we want to write out what charges are we dealing with? What charges do we have in place? Well, start with the manganese ion. When you look at manganese as Mn, write that a little bit more clearly, so we'll rewrite that. So manganese is Mn. When you look at manganese on the periodic table, you don't know what charge it's going to have based upon its position on the periodic table. We have to figure out that charge. Well, this time it's telling us what that charge is. Look at that Roman numeral in the middle. I'm circling in red here. Vi. Well, Vi is the Roman numeral for 6. Now that Roman numeral 6 is telling us what that charge on that manganese has to be. This manganese is +6. So now we can deal with the sulfide. Well, sulfide comes from sulfur. Well, sulfur's S. We look at sulfur on the periodic table. Sulfur on the periodic table resides in group 6A. Things in group 6A, we said, form a charge of -2. So now I have my ions in place. I got the charge from the manganese from the Roman numeral. I got the charge from the sulfur based upon its position on the periodic table. What do I still have to do? I have to achieve charge balance. I'm at +6 -2. How can I achieve charge balance? Well, I'm clearly short negative charges. So I'm at +6 -2. I need to start adding in negative ions. So I'm going to add in another sulfur. What am I at now? Well, now I'm at +6 -4. Well, closer, but I still haven't achieved charge balance yet. I'm still short negative ions. What will I have to do? I will have to add in another negative ion. Now I have charge balance. My sum total of positive charge is +6. My sum total of negative charge is -6. So now I can write the formula for my compound. Positive ion goes first. How many manganeses do I have? I just have one. Negative ion second, that's the sulfur. How many sulfurs do I have? I have 3. So my final formula is MnS3 for this name. Remember, you want to be comfortable going in both directions. Formula to names and the opposite, names to formulas. Our next set of examples involve ionic compounds that contain polyatomic ions. So a little bit before we start getting into some examples of the polyatomic ions, it is absolutely critical that you memorize the names and the formulas of the polyatomic ions. There's no way of getting around knowing them. If there's an alternate to just kind of memorizing these, I would let you know, but you really just have to get these memorized. There's no way of kind of getting around that fact. And generally, the sooner that you know them, the easier the material becomes, because the reason why that is you have to know what they are. These are the factoids before you start using them in order to answer questions and solve problems. So let's look at some ionic compounds that contain these polyatomic ions. So here's our example, NaNO3. How do we know this has that polyatomic ion? Well, you memorized it. You recognize that, hey, when I see that NO3, I want to be thinking, I have a polyatomic ion that I need to deal with. There's our polyatomic ion. So when we deal with these polyatomic ions, the key thing for dealing with a polyatomic ion is that we keep it together. That's what it means. Polyatomic means many atoms. This is a single ion that, as a group of atoms, has a charge. So it's a group of atoms that, as a group, have a charge. So we always want to think about keeping those pieces of a polyatomic ion together. So when we name this ionic compound, we're still going to write our ions. Well, first ion's pretty easy to write out. It's the sodium ion. We recognize that. Group 1A, going to have a charge of +1. Now, for nitrate, we have to recognize that that NO3 is that polyatomic ion. We keep it together. We're not splitting it into a nitrogen and 3 oxygens. It stays together. And as a group, this collection of atoms, NO3, has a charge of -1. We need to keep that together. We're not splitting it up. If you split it up, you'll never achieve charge balance, and there's no way of really fixing that. You have to absolutely keep that together. So now when we name this, we follow the kind of same procedure we did before. Positive ion comes first, keep the name of the element, that's sodium. Then we name the negative ion second. Now, usually you would take the name of the element and chop off the ending and replace it with IDE. Well, a little bit different procedure for the polyatomic ions. For these polyatomic ions, each polyatomic ion has a specific name. You just use that name. You use its name. You say what it actually is. NO3 minus, you memorize, has a charge of nitrate. This compound is sodium nitrate. That's our name of our compound. No more, no less. So the key thing in being able to deal with these polyatomic ions is you just have to spend the time memorizing them. Again, probably a 3x5 index card to make a flashcard for yourself. Name on one side, formula and charge on the opposite side. If we do another example of an ionic compound that has polyatomic ions, we'd be looking at K2SO4. Well, how do you know you have that polyatomic ion in there? Well, You're memorizing the polyatomic ions such that you can recognize them and know what to do with them in formulas and compounds. So we see that polyatomic ion in there. So let's write out our ions again, just as we've done before. I have 2 potassium ions. When we look at potassium on the periodic table, potassium is in group 1A for a charge of +1. That SO4, we recognize that as a polyatomic ion, and you would have memorized this. SO4 will have a charge of -2. Now we're able to write the name of this compound. Positive ion first, that would be the potassium. Negative ion second. Here for the polyatomic ions, you're just going to use the name for that polyatomic ion. SO4 2- is sulfate. You would have had that memorized. So the name of our compound here is potassium sulfate. We have to be very, very careful with these polyatomic ions. So I know I've stressed it a lot already, but you need to take your time to memorize them and memorize them very, very well. You have to be very, very careful with these. The reason why you have to be very, very careful with these is small, subtle differences mean big changes. So just one example, and there's other ones that I could have pointed out, but just kind of one idea to kind of warn you about making sure you're being careful and knowing these well are the eighths versus the ites. These are different by a single letter. They have similar formulas, but they're a little bit different. An example is nitrate is NO3-, but nitrite is NO2-. That's how careful you have to be when you are memorizing these. Also, some polyatomic ions have names that are close to the name of a monoatomic ion. Well, you compare nitrite versus nitride. Well, the difference in those 2 words is by a single letter. It's a D versus a T. Very, very similar sounding names. However, the formulas couldn't be more different. Nitrite, polyatomic ion, NO2-, nitride, monoatomic ion, N3-. So you just have to be very, very careful with these. You really need to spend time and memorize these well. Otherwise, it's very, very easy to make mistakes on these. So we didn't quite get at the last rule yet. That's coming up in our next example. That's rule 4. So we dealt with rule 1, rule 2. We did transition metals for rule 3. Rule 4 applies to the polyatomic ions. And it's the if rule. If there's more than one of the polyatomic ion present. So far, previous examples, you only saw one of the polyatomic ion. If you have more than one, you need to use parentheses around the polyatomic ion and place the subscript outside the parentheses. That way you're very clear to the person looking at it what you actually have in place. And we're going to do an example of that. So an example of this also gives us a chance to practice going the opposite way for some of these. Starting with the name, writing out that formula. So calcium hydroxide. How are we going to write the formula for this? Well, we're dealing with an ionic compound, metal, polyatomic ions, so we're definitely dealing with an ionic compound. We want to write out what ions we have. Well, calcium, we know calcium. Calcium we look at on the periodic table. It's in group 2A. Things in group 2A have a charge of +2. Hydroxide. Well, hydroxide is one of those polyatomic ions. You just have to know the formula and charge for that. You have to memorize it. There's no way to deal with this except to have that memorized. The formula and charge for hydroxide is OH with a negative charge. Now, just like before, all ionic compounds have to have charge balance. These are not an exception. These still have to have charge balance. And when you look at what you have right now, do you have charge balance? And the answer is no. I'm at +2 and -1. How can I fix that? I need to add another one of these negative ions. So I add another one of the hydroxide ions. Now I'm at +2 and -2. Now I have that charge balance. Now I can write out what my formula is going to be. Well, positive ion first, negative ion second. Here's where that parenthesis rule gets used at. If you just kind of randomly put a 2 there, thinking, oh, the reader's going to understand that I'm really referring to 2 units of hydroxide, well, that's not being clear. So we don't want to do that. Instead, whenever we have more than one of our polyatomic ions, instead what we need to do is start off the same way. Calcium, we still have our hydroxide, but now to clearly show that we have 2 of these hydroxide ions, we would place the polyatomic ion in parentheses and put the subscript outside the parentheses. Now you're being perfectly clear what you have. You know, we use parentheses here just like you would use parentheses in writing to put things as a group, or parentheses in math to group things together. Now this is the correct way of writing this. Now you can kind of see, okay, get rid of that, what we had before, the incorrect way of doing it. Now it's very clear what we have. We have 2 hydroxide ions in here. So anytime you have more than one of those polyatomic ions, you need to use parentheses in order to clearly indicate that. The subscript goes outside of the parentheses. So the next couple examples that we want to do aren't necessarily anything new or using a new rule. It's just combining a couple of things we've already have done. We've talked about transition metals. We've talked about polyatomic ions. Now I'm just going to do an example that has both of them present in the same compound. How do we deal with that? Well, all the same rules apply, but let's look at an example of doing this. First, we're recognizing we're dealing with an ionic compound. We recognize that because we have a metal that's going to form a positive ion, and we recognize we have one of our polyatomic ions. This one forms a negative ion. So I can see I'm going to generate positive and negative ions out of this. So whenever we have an ionic compound, we want to write out what are the ions, what are those charges. So for the positive ion, the titanium, so Ti, I don't know the charge right away. All I know is that I have one of them. So I can't figure out the charge right away because it's a transition metal ion. It's there in the middle of the periodic table. I'm not sure what it's going to do yet. I'm going to have to figure it out. Now I'm going to have to figure it out based upon what's happening with the negative ions. So I have 2 of these CO3 polyatomic ions. Here's one where you got to know the charges of these polyatomic ions. If not, you're stuck and you're not going to be able to complete this problem. CO3, you're memorizing this, has a charge of -2. So now I can use the information from the negative ions to figure out what the charge on the titanium has to be. I still need charge balance. What's my sum total of negative charges? Well, -2 and -2 make -4. That means my titanium has to have a charge of +4. in order to have charge balance. So now I'm ready to write my name. Well, positive ion first. Let's get our titanium in here. Positive ion first. Negative ion second, CO3 2-, that's the polyatomic ion that you have to have memorized. You have to know the name of that. That one is carbonate. And now, since titanium is a transition metal ion, I need to use a Roman numeral to indicate the charge. Titanium has a charge of +4, so I need the Roman numeral 4 here. Well, the Roman numeral 4 is IV. Remember what that Roman numeral is telling you. That Roman numeral is telling you what is the charge of that transition metal ion. That's its meaning. So our name for this compound, titanium 4 carbonate. Let's look at another one. Again, another example that just contains both a transition metal ion and a polyatomic ion. So this one, chromium 3 chloride. How do we know we're dealing with an ionic compound? Well, I see chromium, that's a metal. Chlorite, that's one of those polyatomic ions that has a negative charge that I have memorized. So I see my positive ions coming from the chromium, my negative ions coming from the chlorite. So I'm still dealing with an ionic compound. Whenever you're dealing with an ionic compound, you want to write out the ions. Well, chromium is Cr. So chromium Cr, and when I find it on the periodic table, it's a transition metal ion. I don't know its charge right away, but the name is telling me that charge. That Roman numeral 3 that you see in the name, that is what is telling us that we have a charge of +3. Now chlorite, chlorite's one of those polyatomic ions that you're going to have memorized. The formula and charge on chlorite is ClO2 with a -1 charge. So now I have the type of ions that I have. Now I'm looking at how can I achieve charge balance. I'm looking at chromium +3 total positives. My total negatives are only -1. So I need to get more negative ions in here in order to achieve that charge balance. So I'm at +3 -1. I'm going to add another negative. Now I'm at +3 -2. I need to add another negative. So now I'm at +3 -3. Now I'm ready to write my formula out. I have 1 chromium. Now for my chlorites, remember, here I have a polyatomic ion. I have more than one of them. When I have more than one of them, I need to set it in parentheses and get my subscript outside of the parentheses to clearly show how many of that polyatomic ion I actually have. So my final formula for this will be CrClO2 3. So those were the ionic compounds. We have a different type of compound that we're going to name. We also need to name our covalent compounds. Sometimes they go by the term molecular compounds. A similar set of rules, which is both good and bad. It's similar because it helps in memorizing them. It's a little bit bad in that it's easy to mix up. Am I dealing with ionic or am I dealing with these covalent molecular compounds? So here are the rules we're going to apply. We're going to name the first element. Keep the name of the element. We're going to name the second element. Replace the ending with IDE. Third rule is an always rule. We will always use a prefix to describe how many of the second element is present. And then the fourth rule, if there's more than one of the first element, we'll end up using a prefix. Something to notice about this. Nowhere on here are we talking about ions. And the reason we're not talking about ions is because for covalent molecular compounds, ions don't exist. So we really have to make that clear. Remember, no ions for these. We're not looking at ions. We're not looking at charges. We saw this slide before. We dealt with the ionic compounds in the first part of this video. Now we're looking at the covalent or the molecular compounds. Key things here: no ions. We spent pretty much almost an hour talking about ionic compounds and ions. Now you have to get rid of all of that. You can't think about ions at all because there are no ions present. What's holding these compounds together, what's holding the pieces together, is a sharing of the electrons. You're going to be able to identify these covalent molecular compounds from the ionic compounds, again, based upon what elements are in play. Your key thing that you're looking at here, two nonmetals bonded together. That's your clue that you're dealing with these covalent molecular compounds. Let's look at some examples. I'm going to do these kind of side by side. First off, do we recognize that we're dealing with molecular compounds now instead of ionic compounds? The answer should be yes. We can see that based upon the elements that are involved. I look at the example on the left, carbon and oxygen, both nonmetals. The example on the right, carbon and oxygen, both nonmetals. So I kind of want to do these two in parallel so you can see we're always going through the first three rules regardless. So let's go ahead and do this. First off, molecular compound, two nonmetals. What does that mean? That means that we are not writing ions. Do not write ions here because they don't exist. There are no ions in these compounds. So what does the rule say? Well, the rule says name the first element. Keep the name of the element. So the first element is carbon on the example on the left. And if we look at the example on the right, the first element is carbon. Write that a little bit smaller just to make sure we have room to get in the second part. Okay. Next rule says name the second element, replace the ending with IDE. Well, the second element in each case is oxygen. So we're going to chop off the ending, replace that ending with IDE. So the oxygen is going to become oxide for the example on the left. For the example on the right, same thing. Oxide. Right now you're going to notice that we have a problem. Just using the first two rules, we have the same name for both of these compounds. That's a big problem. We have to have a way of differentiating these. These are very, very different compounds. So different that one of them, the compound on the left, is required for life, CO2. The compound on the right is very, very deadly and a dangerous poison. We definitely want to be able to differentiate between these two and not mix them up. That's where rule 3 comes in, or step 3 comes in. That's not always rule. You will always use a prefix for the second element. Let's just kind of quickly go through our prefixes. Prefix for 1 is mono, 2 di, 3 tri, 4 tetra, 5 penta, 6 hexa, 7 hepta, 8 octa, 9 nona, 10 deca. So the example on the left, how many oxygens do I have? Well, I have 2 oxygens on the left. The prefix for 2 is di. So this becomes what you're very familiar with. Compound on the left is carbon dioxide. Now if we look at the compound on the right, we have one oxygen. The prefix for one is mono, and this is just an English thing. You end up chopping out one of the O's. If you leave the other O in there, it makes the word sound weird. So carbon monoxide, your CO detector in your home, your carbon monoxide detector to alert you if any of this compound is present. So we now have a way of differentiating it. And we have that way because of that third rule, that always rule. That rule that says you will always use a prefix to describe how many of that second element you have present. We look at another example of a molecular compound, P2S5. Again, we look at the elements involved. We look at phosphorus. When we're looking at phosphorus, it's a nonmetal. When we're looking at sulfur, it's a nonmetal. So we have two nonmetals here. That's what's telling us that we're dealing with a molecular compound. So we're going to go through and we're going to name this. Remember, no ions in place here. We're not writing out any ions. Write the name of the first element, keep the name. The name of the first element is phosphorus. Second element, sulfur. Replace the ending with the IDE. That's going to make that sulfide. Second element always gets a prefix. So for sulfur, we have 5 of them. So the prefix for 5 is penta. Now the first element will only get a prefix if there's more than one. If you look back at the previous examples we did with the carbon monoxide, carbon dioxide, we only had one of the first element. We didn't use a prefix. Here, for that first element, that phosphorus, we have more than one of them. We have 2 of the phosphorus there. When you have more than one, you have to use a prefix. So the prefix for 2 is di. So here you're looking at diphosphorus pentasulfide. So the second element always gets a prefix no matter what. The first element will only get a prefix if you have more than one of them. So in this example, just like before with the ionic compounds, we want to be able to go both ways. Formula to name, name to formula. So here's an example going that opposite direction, starting with the name, having us write out what that formula is. So the name we're looking at is dinitrogen tetrabromide. Well, first, are we really dealing with a molecular compound? Well, when you look at nitrogen on the periodic table, it's a nonmetal. When you look at bromine on the periodic table, that's also a nonmetal. So we have our 2 nonmetals in place. So we're definitely dealing with a covalent compound, a molecular compound. So we're not going to write ions, but first element that we have is nitrogen. How many of them do we have? Well, we're going to have 2 of them. We figured that out from the di prefix out in front. Second element, bromide, well, that's really from bromine. How many of them do we have? Well, the tetra in front tells us that tetra is a prefix for 4. So our formula will be N2Br4, dinitrogen tetrabromide. 2 nitrogens, 4 bromines.